Hi, I'm Harry and welcome to Science News. In 1900, the British physicist Lord Kelvin is said to have pronounced, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." Within 3 decades, quantum mechanics and Einstein's theory of relativity had revolutionized the field. Today, no physicist would dare assert that our physical knowledge of the universe is near completion. To the contrary, each new discovery seems to unlock a Pandora's box of even bigger, even deeper physics questions. These are our picks for the most profound open questions of all. Inside you'll learn about parallel universes, why time seems to move in one direction only, and why we don't understand chaos. So let's talk about the 7 biggest unsolved mysteries in physics. Number 1. What is dark energy? No matter how astrophysicists crunch the numbers, the universe simply doesn't add up. Even though gravity is pulling inward on space-time, the fabric of the cosmos, it keeps expanding outward faster and faster. To account for this, astrophysicists have proposed an invisible agent that counteracts gravity by pushing space-time apart. They call it dark energy. In the most widely accepted model of dark energy, it is a cosmological constant, an inherent property of space itself, which has negative pressure driving space apart. As space expands, more space is created, and with it, more dark energy. Based on the observed rate of expansion, scientists know that the sum of all the dark energy must make up more than 70% of the total contents of the universe. But no one knows how to look for it. The best researchers have been able to do in recent years is narrow in a bit on where dark energy might be hiding. Number 2. What is dark matter? Evidently, about 84% of the matter in the universe does not absorb or emit light. Dark matter, as it is called, cannot be seen directly, and it hasn't yet been detected by indirect means, either. Instead, dark matter's existence and properties are inferred from its gravitational effects on visible matter, radiation and the structure of the universe. This shadowy substance is thought to pervade the outskirts of galaxies, and may be composed of weakly interacting massive particles, or WIMPs. Worldwide, there are several detectors on the lookout for WIMPs, but so far, not one has been found. One recent study suggests dark matter might form long, fine-grained streams throughout the universe, and that such streams might radiate out from Earth like hairs. Number 3. Why is there an arrow of time? Time moves forward because a property of the universe called entropy, roughly defined as the level of disorder, only increases, and so there is no way to reverse a rise in entropy after it has occurred. The fact that entropy increases is a matter of logic. There are more disordered arrangements of particles than there are ordered arrangements, and so as things change, they tend to fall into disarray. But the underlying question here is, why was entropy so low in the past? Put differently, why was the universe so ordered at its beginning, when a huge amount of energy was crammed together in a small amount of space? Number 4. Are there parallel universes? Astrophysical data suggests space-time might be flat, rather than curved, and thus that it goes on forever. If so, then the region we can see, which we think of as the universe, is just one patch in an infinitely large, quilted multiverse. At the same time, the laws of quantum mechanics dictate that there are only a finite number of possible particle configurations within each cosmic patch, 10^10 to the power of 122 distinct possibilities. So, with an infinite number of cosmic patches, the particle arrangements within them are forced to repeat infinitely many times over. This means there are infinitely many parallel universes, cosmic patches exactly the same as ours containing someone exactly like you, as well as patches that differ by just one particle's position, patches that differ by 2 particles' positions, and so on down to patches that are totally different from ours. Is there something wrong with that logic, or is its bizarre outcome true? And if it is true, how might we ever detect the presence of parallel universes? Check out this excellent perspective from 2015 that looks into what infinite universes would mean. Number 5. Why is there more matter than antimatter? The question of why there is so much more matter than its oppositely charged and oppositely spinning twin, antimatter, is actually a question of why anything exists at all. One assumes the universe would treat matter and antimatter symmetrically, and thus that, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced. But if that had happened, there would have been a total annihilation of both. Protons would have cancelled with antiprotons, electrons with anti-electrons, positrons, neutrons with antineutrons, and so on, leaving behind a dull sea of photons in a matterless expanse. For some reason, there was excess matter that didn't get annihilated, and here we are. For this, there is no accepted explanation. The most detailed test to date of the differences between matter and antimatter, announced in August 2015, confirm they are mirror images of each other, providing exactly zero new paths toward understanding the mystery of why matter is far more common. Number 6. What is the fate of the universe? The fate of the universe strongly depends on a factor of unknown value, omega, a measure of the density of matter and energy throughout the cosmos. If omega is greater than 1, then space-time would be closed like the surface of an enormous sphere. If there is no dark energy, such a universe would eventually stop expanding and would instead start contracting, eventually collapsing in on itself in an event dubbed the Big Crunch. If the universe is closed but there is dark energy, the spherical universe would expand forever. Alternatively, if omega is less than 1, then the geometry of space would be open, like the surface of a saddle. In this case, its ultimate fate is the Big Freeze, followed by the Big Rip. First, the universe's outward acceleration would tear galaxies and stars apart, leaving all matter frigid and alone. Next, the acceleration would grow so strong that it would overwhelm the effects of the forces that hold atoms together, and everything would be wrenched apart. If omega equals 1, the universe would be flat, extending like an infinite plane in all directions. If there is no dark energy, such a planar universe would expand forever but at a continually decelerating rate, approaching a standstill. If there is dark energy, the flat universe ultimately would experience runaway expansion leading to the Big Rip. Regardless how it plays out, the universe is dying, a fact discussed in detail by astrophysicist Paul Sutter in the essay from December 2015. Number 7. Is string theory correct? When physicists assume all the elementary particles are actually one-dimensional loops, or strings, each of which vibrates at a different frequency, physics gets much easier. String theory allows physicists to reconcile the laws governing particles, called quantum mechanics, with the laws governing space-time, called general relativity, and to unify the 4 fundamental forces of nature into a single framework. But the problem is, string theory can only work in a universe with 10 or 11 dimensions, 3 large spatial ones, 6 or 7 compacted spatial ones, and a time dimension. The compacted spatial dimensions, as well as the vibrating strings themselves, are about a billionth of a trillionth of the size of an atomic nucleus. There's no conceivable way to detect anything that small, and so there's no known way to experimentally validate or invalidate string theory. Thanks for watching this video. For more details, please visit www.widelyexplore.com.